Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we were discussing about the memory management. Today we will extend our concepts to the further techniques which are used for the memory management. In the earlier lectures, we have used the techniques which were having a lot of fragmentations. So, we shall try to understand some of the techniques which may have the least fragmentation. Now, the outline of today's lecture would be that we will first have a quick recap of whatever we have discussed on the previous turns of the memory management, and then we will look at a technique known as paging, and we will also see how the address translation is done in the paging. Now, to have an understanding about the memory management technique, it is very essential to have a knowledge about the logical and the physical addresses, and the logical address space and the physical address space. Whenever a CPU is referring to any instruction of any process, then CPU views every process as a separate entity, and let us say there are 200 instructions in the process. So, the addresses of those instructions will be from 0 to 199. So, any address in between 0 to 199 is actually referred to as the logical address or the virtual address. So, this is the address generated by the CPU. When this program or when this process is accommodated into the main memory, it gets the physical space, and that physical space may be in any part of the memory. Whichever part is free, the process will be accommodated there. It means the process is relocated to any of the region in the memory. So, we should have a knowledge about the base address or the place from where the process first instruction is getting started stored. So, let us say the first instruction of this process in the main memory is getting stored at the address, let us say 10,000. So, the last address for this particular process will be 10,199 in case we are considering that the contiguous allocations are taking place. This address or any address in between 10,000 to 10,199 is known as the physical address. So, the physical address is the address of the main memory, address of any instruction in the main memory. So, CPU is referring to the logical address, and that process is getting stored somewhere in the physical memory or the RAM. So, the address of the desired instruction in the main memory will be the physical address. Now, we may be dealing with lot of processes in the system. The largest process let us say has a size x. So, the addresses will be from 0 to x minus 1. So, anything in between 0 to x minus 1, this is actually known as the logical address space, and let us say the physical memory is of 2 GB. So, any address in between 0 to last address in the main memory is known as the physical address space. So, the space is very large, and in this large space your process may fit anywhere. Now, we have discussed about the contiguous and the non-contiguous schemes. We have seen about the two schemes by which the contiguous allocation can be done. One is the multi-programming with the fixed partitioning, and the other scheme was the dynamic partitioning. In the fixed partitioning, there were two schemes. One scheme was suggesting to create the equal size partitions. Let us say the main memory is of 800 kilobyte. So, 8 equal parts can be created of size 100 each. So, this becomes the equal partitioning. So, each of the slot in the main memory is of size 100 kilobyte. Similarly, unequal size partitions can also be created, and in the unequal size partitions, all the partitions are of the unequal size. Let us say one of the partition is of 30 KB, one is of 50 KB, another one is of 200 KB, another one may be of 150, and so on so forth. So, here also we are fixing up the degree of multiprogramming, meaning that how many processes can come in the main memory. Let us say in the equal partitioning scheme, a process of size 60 KB is coming. So, if a process of 60 KB is coming, it means we have a wastage of 40 KB in first slot. Similarly, let us say a process of 80 KB is coming, then we have again a wastage of 20 kilobyte. So, in each of the partition it is expected that there will be some fragmentation or some space which will remain unused, and this unused space is known as the fragmentation, and in the fixed partitioning scheme we cannot reuse the free space available. So, that is the sheer wastage of the memory. Since this is a wastage of memory, we are saying that this is the internal fragmentation. And in the dynamic partitioning scheme, we have lot of space, lot of processes depending on the requirement being allocated to the main memory. When the process exits, a hole is created, and when a process comes, process goes, another process comes, another process goes, lot of holes are created. Since lot of holes are getting created, it means we have lot of fragmented space in the main memory. It may so happen in the future that a process comes and process is not getting or process is not able to fit into any of the holes there in the main memory, but the cumulative size of the holes may be sufficient enough to accommodate the process. For example, let us say we have 3 holes in the system, and in this let us say we have a hole of 30, we have a hole of 50, and we have a hole of 70. So, we have cumulatively 150 kilobyte space. A process of size let us say 90 kilobyte comes. So, 90 kilobyte process can be accommodated if all these holes are brought together, but individually they are not able to fit the process. So, a compaction scheme is required in this case to bring all the allocated space on one side and all the free spaces on another side. So, this is causing us the this dynamic partitioning is causing us the external fragmentation, and to remove the external fragmentation we may use the concept of the fragmentation. We also have seen that the fragmentation is a very costly scheme. When the when the fragmentation takes place, then the CPU is completely busy in doing the relocation works only, and it is not able to execute any process at that moment. So, lot of CPU time is getting wasted in this effort. So, this is just an example of what we have discussed, the equal size partitioning and unequal size partitioning, and the dynamic partitioning, wherein the processes can come in to the main memory as per the requirement. We are considering that the user space in the main memory is treated as a single hole in the beginning, and as soon as the processes start coming, they are given the space as per their requirements. So, the degree of multiprogramming is not getting fixed here in the dynamic partitioning. It was also seen that when we are dealing with the dynamic partitioning, and since the dynamic partitioning is allowed and the processes can exit at any point of time, let us say the J2 process completes and there is a hole just below this. So, when J2 process exits, there is a hole, another hole being created. So, these two holes which are adjacent to each other, they get automatic merging. So, automatic merger of the holes are allowed here in the dynamic partitioning. This you can see as an advantage also, that when the holes are created, they are just to reduce the number of the holes, we are accumulating the nearby holes. So, as a part of this means if we are doing this kind of the operation where the automatic mergings are taking place, on an average it has been seen that there will be half holes than processes. Let us say there are x processes, then there will be x by 2 holes. It means 1/3 memory is used or occupied by the holes. 1/3 memory is occupied by the holes. This is known as the 50% rule, or we can also say that this is the 1/3 memory rule. It can be referred to as both the things, the 50% rule or 1/3 unused memory rule. Now, we have also discussed about the segmentation. We have seen that the segmentation is a scheme that is not the contiguous memory allocation scheme. This is the user, this actually creates the user view of the program. You can see that in your program there may be main program, procedure, function, methods, objects, many more things, symbols, arrays, stacks. So, all these are considered as the segments, and when we allocate the memory to the process, these segments go into the different portion of the memory. So, this is unequal size partitioning scheme, wherein we are not accommodating the entire process in the contiguous space, single contiguous space, but the segments are created and segment go into different part of the memory. Now, when the segments are going into the different part of the memory, we need to keep track of all those segments. So, for keeping track of those segments, we maintain a segment table. Now, this segment table stores the segment number, the base means from which location in the memory this segment is getting stored, and what is the size of the segment. So, length is known as the size of the segments. So, let us say here the 0 number segment is going in the 1400 address in the main memory. It has a address or it has a length 1000. So, 14,000 is the first address and last address will be 14,999 from the this is 1400. So, this 999 will be added. So, this will be 2399. So, 2399 will be the last address of this segment number 0. Similarly, segment number 1 will go in the main memory at the address 6300. So, segment number 1 will go there. Whenever we have to access to any address in the segment, then the this kind of the hardware is used, wherein the CPU is generating the logical address. This has two components, let us say segment number and offset. We divide the address into two parts, segment number and offset. The offset is checked. Offset means which address we are going to refer to. So, that has to be in the limit, means we already have defined the limit here. You can see this, the length of the segment is decided. If we are referring that the length of the segment is 1000, so the only addresses can be 0 to 999. Okay. So, this length or the limit in the segment table is actually referring to the length of the segment or size of the segment. So, offset referred should be less than the segment number, segment size. So, if it is so, we will refer to other part or we will go for the other part. Otherwise, if this is not less than, it means this is the addressing error. So, you will throw the addressing error from here. Fine, let us say the address is correct, then you have to add the base in the address referred or the offset referred, and this will be giving you the actual location of the instruction in the main memory, and you can send it through the CPU for the execution. So, this was all about the segmentation and all of the schemes that we have discussed so far. We will now see a technique which actually will cause the less fragmentation. First, start with understanding what is the problem with the segmentation also. The problem with the segmentation is that let us say a segment of size 1000 has got accommodated in the, let us say segment number 0 has got accommodated in the main memory. Now, it leaves. When it leaves, the another segment will come of, let us say some other process. If another segment comes, that may not be of the same size 1000, let us say that segment is of size 700. So, that 700 size segment will come here, which will create a whole of 300 size. So, that means once again we have the fragmentation. So, we have small fragmented spaces when we are using the segmentation scheme. So, segmentation scheme is also causing us the fragmentation. So, we do not want the fragmentations to take place. So, the next technique that we are going to study will actually not cause any kind of the fragmentation. This scheme is known as the paging scheme. So, what does the paging scheme say? The paging scheme says that I have a process, let us divide it into the small chunks of equal size and we will call them the pages. In the main memory also we will create the same size chunks and we will call them the frames, and the pages of the process will fit into the frames. So, when the pages will fit into the frame, there will be no wastage in the frames. Okay. Let us take an example. Let us say we have 100 byte size process, okay, and then we are going to divide it into the pages of, let us say 20 size. It means 20 bytes will be accumulated together and we will call them a page. Fine. So, there will be 5 pages in this process, and we have a main memory, and the main memory we have 20 byte size frames. So, all these frames, all those 5 frames which are there in the process, they will be getting fitted into any part of the memory which is free. Okay. So, this will be getting fitted into the any part of the main memory which is free. So, they will be fitting in the frames. So, if 20 byte block is adjusted in the 20 byte block itself or 20 byte frame, so obviously there will be no wastage. So, for all the process we will be doing so, equal size pages will be made and those pages will be getting fitted into the main memory frames. Let us see this with an example. Let us say we have the process, let us say the process has 16 bytes. Let us say the process has 16 bytes or the size of the process is 16 bytes, and we have divided these 16 bytes into, let us say, a 4 byte page. So, the page number 1 contains 4 bytes, page number 2 contains another 4 bytes, page number 3 contains another 4 bytes, and page number 4 contains the last 4 bytes. So, the first 4 bytes are referring to my first page and I will call that a 0 number page. Okay. And then the next 4 bytes will be said to be the page number 1, next 4 byte will be said to be the page number 2, and the last 4 byte will be referred to as page number 3. So, we always start the address with the 0, that we should consider always. Here is the main memory, this is the main memory. In the main memory we are going to create the equal size chunks again. So, 4 byte or slot of 4 bytes is accumulated together and we are calling that this is the frame number 0. Okay. This was page number 0. In the process we will have page. So, page number 0, page number 1, page number 2 and page number 3 in the process, and frame number 0 and then frame number 1 that also contains 4 bytes or 4 addresses, and the frame number 2 that is also containing 4 addresses, and so on so forth. We are dividing the frames like this only. Now, one page will be able to accommodate in one memory frame. So, there are two terms to remember here, one is the page and the other one is the frame. Pages do get adjusted into the frames. Frames are there in the main memory and the pages are there for the process. Page and the frames are of the equal size. Okay. Now, let us see this. We have represented the same thing in the different way. Let us say the process is of size 32 bytes. We are saying that a page is of size 4 bytes. So, when the page is of 4 bytes, we divide it by 4, then we will have 8 different pages. We will have 8 different pages. So, we have page number 0, page number 1, 2, 3, 4, 5, 6 and 7. So, this is one page and the one page is containing bytes 0, 1, 2, 3. Second page is containing byte number 4, 5, 6 and 7, and this page number 2 is containing 8, 9, 10, 11 number bytes, and then the third is page number 3 is containing 12, 13, 14 and 15 and so on so forth. There will be 8 different pages, they are numbered from 0 to 7. Similarly, in the main memory we have created the frames. So, this all are the frames and all these frames are of size 4 byte each. Okay. Let us number these frames. This is frame number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Now, these pages will are getting accommodated in the main memory frames. So, the location of these are the page number 0, which is containing byte number 0, 1, 2, 3 has got adjusted in frame number 5. You can see here the byte number 0, 1, 2, 3 is getting accommodated in the frame number 5. I have encircled this also and put a tick mark as well. So, I know that the page number 0 has got adjusted in the frame number 5. So, let us maintain a record of this as well somewhere. Similarly, page number 1, which is containing byte number 4, 5, 6 and 7. So, byte number 4, 5, 6, 7 is getting accommodated in the frame number 11. So, we have the page number 1 which is getting accommodated in the frame number 11. Similarly, we have page number 2. So, page number 2 is getting accommodated in frame number 1. Here we have, let us put a tick mark here. So, page number 2 is getting accommodated in the frame number 1. Similarly, page number 3 is getting accommodated in the frame number where it is 12, 13, 14 and 15. So, this is in frame number 15. So, we maintain a record for this as well. Now, page number 4 is getting accommodated in frame number 7. So, we are maintaining a record of this as well. Page number 5 means 20, 21, 22, 23. This is getting accommodated in the frame number 13. Similarly, page number 6, which is containing byte number 24, 25, 26 and 27. This is getting accommodated in frame number 3. Similarly, page number 7, which is containing byte number 28, 29, 30 and 31. This is getting accommodated in frame number 9. So, we have adjusted the pages into the frames. This is the first thing. The second thing is that we are maintaining a record of all these adjustments. Fine. So, the record is maintained in a table known as the segment table. Obviously, we will need a segment table per process. For every process, we will need a segment table which will map the page into the frames. Fine. Let us say we want to refer to any of the page in the process. Okay. We want to refer to any of the page in the process. I already have told you that these pages have been given a number 0 to 7. Okay. Now, let us consider that the earlier example was taken. Let us say we are taking a very small example. Let us say we have 4 bytes in our process. In case we have 4 bytes in our process, the addresses may range from 00, 01, 10 and 11. It means there will be 4 bytes, and for those 4 bytes the addresses are like this. So, 2-bit address will be there, it means 2 square. So, whatever is the power of 2 is telling us the number of bits in the address. Similarly, let us say we have 8 bytes. The 8 bytes are there, then the addresses would be 000, 001, 010, 011 and so on and so forth. Last will be 111. So, the address is of 3 bits. Okay. In the example that we took here, we have 32 bytes in a process. So, in case we have 32 bytes in a process, the 32 bytes can be referred to with a 5-digit address 0000, 00001, 00010 and so on and so forth. Last one will be 11111. So, 5-bit address will be there for 32 pages. So, 32 bytes. Okay. Then what we have done, all the 32 bytes have been divided into a 4-byte page. Okay. So, the number of pages are 8. The number of pages are 8, those pages can be numbered as 0, 1, 2, 3 and so on and so forth 7. Since this is 8, so 2 cube means 3-bit can be specified for referring to the page number. Okay. So, if you consider that the 32 byte is there in my page, then this is 8-bit, sorry 5-bit is specified for addressing to any byte, out of which 3 bits are used to refer to the page number. Okay. This is page number. Why 3 bits? Because there are 8 pages. 8 pages will be numbered as 0 to 7, and if you write in the binary, then 0 to 7 can be represented in 3 bits. Fine. So, if you take 8 represented in the power of 2, the power is telling you that how many bits will be there to represent a page number. Now each page is of size 4 byte. Okay. To refer to any of the bit from the 4 bytes, you need 2 bits. We already have discussed this. Okay. So this is known as the offset, D or offset. So we have a page number and we have a offset. So we have divided the address into 2 parts. One is the page number and the other one is the offset known as the D. For this particular example that we have taken, 3 bits are used for page number and another 2 bit is used to refer to the offset within the page. Okay. So offset within the page means what? Let us say we are going to this example again. Let us say we want to refer to this byte. Okay. So this byte is what? This byte is 0, 1 and then 2. It means this is byte number 10. Okay. Let us say we are going to refer to this one. So in page number 4, this is referring to byte second. Second means 1. 0 के बाद 1 आएगा. And then 1 can be represented as 01. So 01 is the address of this byte. Similarly, let us say in the 6th page, we are going to refer to this 27. So 27 is what? This is the third byte. So third byte can be represented as 11, 0, 1, 2, 3, 3 byte. So 11. Okay. Let us say we want to refer to this. What is this? This is the page number 6 and offset 11. Let us write the address. Page number 6 and offset is 3 or 11, whatever you say. Now page number 6, you can see that the page number 6 from the segment table is going to frame number 3. Okay. So frame number 3. So you are finding out the physical address by this. So frame number 3 is the frame number in the main memory and the offset remains the same, offset remains the 3. So go to the 3 number page, 3 number frame, this is the 3 number frame and in this 3 number frame you refer to the byte number 3, that is referring to 27 byte, and yes, we were referring to byte 27 only in the original process. So the logical address will contain page number and offset, and the physical address will be containing frame number and offset. So this is the physical address. The segment table is helping us to achieve the address translation from the logical address to the physical address. We are maintaining the segment table, sorry, page, this is not the segment table, this is the page table, sorry, this is the page table. So this page table is helping us to achieve the address translation from the logical address to the physical address, and we will be maintaining the page table for each of the memory references, sorry, each of the process. Now this is all what we have discussed, the page number and offset, this is the logical address. If the size of the process is 2 raised to the power m, then there will be m bits in the logical address, which is divided into 2 parts. If the size of the page is 2 raised to the power n, then n bits will be used for referring to the offset, rest of the n minus n bit will be referring to page number. Fine. Now this is the paging hardware that will be used for the conversion of the logical address to the physical address. What we have done here, CPU is referring to the logical address. Logical address is divided into the 2 parts, page number and offset. Now this page number, corresponding to this page number, let us find out a frame number from the page table. So we have found one of the entry in the physical address, that is the frame number. So frame number is being found from the page table. The offset remain the same of the logical address. So this is the logical address, and this is the offset of the logical address. So together we are forming the frame number and the offset, which is the physical address. Now this physical address is the address of your instruction in the main memory. You go to that part of the main memory, give the instruction to the CPU for the execution. So this is how we have converted the logical address to the physical address. So we can solve several problems related to the paging, and this part of the paging is one of the most important section of the memory management, and several questions are being asked in the GATE examination, even in your university examination. On a regular basis the questions are being asked from the paging. So, the first thing that you should know that how the address translation takes place. We have discussed it here, that we are referring to the page table for the conversion of the logical address to the physical address. So, this is the reference for this lecture, operating system concepts by Silvershaj and Galvin, and in the next lecture we will discuss about lot of numericals related to the paging. Thank you.